sciences. His research focuses on the intersection between control and machine learning with the aim of developing algorithms and techniques that can endow machines with the ability to autonomously acquire the skills for executing complex tasks. In his talk today, he will discuss research that aims to make learning fully autonomous by enabling robots to improve continuously from experiences they collect on their own, either by attempting tasks in the real world or simply by watching us, humans, acting in our natural environment. The title of his talk is Machines That Learn by Doing. Please welcome him.
All right, thank you very much. So my name is Sergey Levine. I'm a professor at UC Berkeley, and I also spend part of my time at Google Brain. And I'll talk about machines that learn by doing. So by way of introduction, when I was younger, and maybe when some of you were younger, I saw on television and movies and books machines that seemed to exhibit, properties of intelligence that we usually associate with humans. Things like, Rosie the robot, or maybe Baymax, a little more recent. This guy. Maybe those of you that have a more mischievous predisposition, maybe when you were younger, you were inspired by this guy, perhaps, to build machines that are intelligent, that can learn, that can adapt from their own behavior. And I think a valuable exercise to go through is to think about, well, what would it really take for machines to exhibit the kind of flexibility, adaptability, and intelligence that humans have? Because it's more than just analytical reasoning, more than just planning. It's actually the ability to be resourceful, to flexibly adapt to unexpected environments. As an example of a task that is both easy and difficult today, imagine you have this giant oil tanker. You need for this oil tanker to navigate between two destinations. The navigation of the oil tanker is not very difficult to automate. It doesn't require any kind of machine learning. It doesn't require what we would call perhaps artificial intelligence. But you still need people on board the oil tanker, because if something breaks in the engine room, this guy needs to go down there and fix it with a wrench, right? So it's when you meet the physicality of the real world, the messy perception, the complexity, everything unexpected that can go wrong, that's where you need intelligence, resourcefulness, and adaptability. So in the parlance of machine learning, this is basically all about generalization. Generalization to complex, unstructured environments. Deep learning is a technology that helps us handle unstructured environments. And we've seen some really impressive successes in this area in the last few years. So take a giant neural network, train it with large amounts of, let's say, image data, and suddenly you have a system that can recognize objects in natural images, which are an example of an unstructured environment. You can translate text, you can recognize human speech, and so on. But these technologies by themselves don't actually make decisions. They don't actually act resourcefully in the real world. In order to do that, we need to have some kind of mathematical formalism that allows us to reason about decision-making and control. So reinforcement learning provides us one such formalism. At a super high level, the basic idea is that you have your agent. Your agent is going to choose actions, it's going to make decisions, and the real world will produce some consequences, such as observations and the rewards that the agent is trying to maximize. And this lets us reason about how we can cram decision-making and control into the machine learning framework. And in fact, we can combine it with ideas from deep learning to have decision-making systems that can actually scale to complex scenarios. And in fact, we've seen some success of this, going back actually decades to things like TD Gammon in the 90s, all the way to AlphaGo very recently, systems that can learn basic motor skills, robotic control, playing video games, and so on and so on. And these are very impressive. But looking at these examples of kind of the successes of combining reinforcement learning and deep learning, one of the things that might stand out is that the particular domains in which these methods have been successful don't look quite the same as the really messy, complicated, real-world, unstructured settings I showed on the previous slide. So while it's very impressive to be able to beat a human player at the game of Go, the setting itself is very pristine and clean. You never have to worry about what the pieces look like or whether somebody might spill some coffee on the table. The kind of unexpected situations that happen all the time in the real world are abstracted away in these clean and pristine environments. Now, maybe this is just because we haven't tried hard enough, but what might really be going on here? Well, if we dig a little bit deeper, maybe it's not so simple. Deep learning handles unstructured environments using big neural networks and data that looks like this. Millions of images collected from all over the world, mined from the internet and so on, that really illustrate the diversity of the visual world, in this case, for image recognition. So how can we possibly hope for reinforcement learning to enable intelligent machines when it trains on data that looks like this, kind of clean, pristine settings where nothing unexpected ever happens, where things always happen the same way if you do something twice and so on? So maybe we learned the wrong lesson from deep learning. Maybe it's not just about taking deep nets and stapling them onto a reinforcement learning algorithm. Maybe the right lesson to get from deep learning is that it's really not about the deep nets. It's about having large, high-capacity models and highly varied and diverse data. And perhaps one of the things that we're really missing when it comes to deep reinforcement learning is to really bring in those ingredients and see whether we can scale up to complex real-world scenarios that exhibit diversity and variability. Okay, so in this talk, I'll cover 3 topics that I think begin to get at some of these ideas. First, I'll talk about reinforcement learning algorithms that I think might be a little bit more suited for real-world reinforcement learning tasks. There's, I think, huge challenges that still remain, but maybe some of the early steps are starting out there. I'll talk about generalization from large amounts of real-world experience and some real-world robotic experiments that get at this point. And then I'll talk about how we can make it all happen quickly and more efficiently by learning to learn, by using large amounts of diverse past experience, not just to generalize more effectively, but to actually accelerate the process of learning itself. All right, so let's start with the RL algorithms. So reinforcement learning, when it comes to the diversity and complexity of the real world, has a really big problem. To illustrate this problem, let me start by explaining the typical pipeline for a supervised learning system. You start with the real world, as we always do. You go out into the real world and you collect data. You collect a large amount of highly diverse data, like, for example, ImageNet, if you're doing image recognition. And you do this just once. And once you have this data, you can repeatedly train your model on that data. You can train it for many epochs. You can train many different models and pick the best one. And once you achieve the results that you're happy with, then you deploy that model, and hopefully it does something useful. In reinforcement learning, you have your environment. Your agent collects some data from that environment, uses that data to update its model, and in a non-policy algorithm, it simply discards the data, goes back to the world, collects more data, and repeats this process. Now, this by itself might already seem extremely onerous, because if your data has all the complexity and diversity of something like ImageNet, that means you're essentially collecting all of that complex data every time, throwing it in the garbage, and then starting again. And this is done many times. The reality is actually even worse. Actual reinforcement learning doesn't look quite like this. Actual reinforcement learning actually also has an outer loop, and the outer loop is this guy. This is the guy who's trying to design the algorithm, adjust hyperparameters, try to make it work better. Some of you in the audience might feel that some days you are this guy. You've had that experience of this really painful outer loop. And that's even if you're doing something in simulation, something on a toy simulated domain. If this inner loop involves interaction with the real world, and if it involves gathering large and diverse data sets, the outer loop becomes completely impractical, right? So that's not something that you want to repeat every single time you modify something about your method. So one of the ways that we can combine this rich and highly varied data with reinforcement learning is to look at off-policy reinforcement learning algorithms. And there are quite a few techniques that we can start to draw on there. The general scheme here would look something like this. In contrast to the cycle that I have on the left side of this slide, you would start with the real world. You would have a body of past behavior, all the things that you've done in the world in the past, that gives you a large data set to start with. You use this data set for off-policy reinforcement learning to get to some baseline level of performance in your behavior. And then you take this behavior and you go out into the real world a little bit more and occasionally get a little bit more data. And the nice thing about this setup is that first you can have this beginning kind of repository of rich experience that you can use to learn about the diversity of the real world. And if you do modify something about your algorithm, if this guy goes in and changes something, all of the data that's been collected so far can still be reused. And this produces also a much more practical development and research cycle. So how bad is this problem really? Let me show a video here. This is from a paper that we had in 2016. This is a non-policy reinforcement learning algorithm. It's a policy gradient algorithm called trust region policy optimization. And this algorithm is learning to walk. And looking at this video, maybe it's kind of cool. The humanoid robot really learns to walk, and he'll actually learn to walk perpetually without falling once this is all over. It takes a while. This all runs in simulation, but if we were to run this in the real world on a real walking robot, this would take about 6 days of real time if it was running in real time. Okay, that might seem kind of onerous, but maybe not so bad. Like, okay, if you just have to wait 6 days and then you get an awesome walking robot, maybe that's worth the trouble. But this is to run on an infinite flat plane, right? If you want an actual running robot, you want it to run on the road, on the mountains, do parkour, run on the water, whatever. It essentially has to go round robin through all of these different environments, try each of them in turn every single iteration. If you want your car to drive in all the cities in the world, maybe you have to go from city to city every single time you update your policy and then repeat this. So the real world is not so simple, and this kind of scheme clearly is not going to scale. So, okay, we have this idea of using off-policy reinforcement learning where we don't have to basically recollect all of ImageNet every single time if we want ImageNet level generalization, but we can collect the large data set in advance and then build on it continuously. So what's the problem? Well, first, let me briefly describe how off-policy RL works or how it can work, and then I'll describe some of the challenges and some ways we can begin addressing them. So off-policy reinforcement learning at its most basic level is a problem of prediction. And the question you might ask is, well, what do you predict? And you have a few choices. One of the things you can predict is the sum of future rewards, and that's how a wide range of off-policy RL algorithms work. You can also predict future observations, and that's how model-based RL algorithms work. In reality, they're actually not so different, and there's been quite a few prior works that draw connections between these. We have some recent work that also does that if you want to check that out, but that's going to be outside of the scope of this talk. So let me just very briefly summarize a very commonly used off-policy RL algorithm called Q-learning. Many of you might be already familiar with it, so please bear with me, but I just want to make sure we're all on the same page. So in RL, just to remind you all, the agent takes actions. We're going to denote those by A. The real world produces consequences, states S, and rewards R. And our goal in reinforcement learning is to optimize a policy, which is a distribution over actions given states, that maximizes the expected sum of rewards. So we'd like to choose the policy so that the rewards over all time are maximized. Not just the reward right now, but the reward also in the future. And one very useful object for doing this is something called the Q function. So the Q function is a function of the state in action that tells us what is the total reward that you will collect if you start in the current state and take a particular action. And if you can learn a Q function, then you can recover a policy from that Q function by simply taking the action that the Q function tells you is the best. Okay. So if we can just get this Q function, then we can have a policy. So we need to find a way to get a Q function. And there's a very convenient way to do it by using the Bellman backup. So those of you familiar with reinforcement learning probably immediately recognize this, where you say that the optimal Q function is simply the current reward plus the max over the next action of the Q function. And if you can find a Q function that satisfies this equation, then you can recover the optimal policy from it. And the very nice thing about this procedure is that you don't need on-policy data to do this, right? You can have data that comes from any distribution, provided that it has overlapping support with the optimal policy. And you can, if you can solve for a fixed point of this equation, you will have obtained a good policy that solves your task. Question?
Now, in this case, your states are exogenous, right? They're not dependent on the action, but there's given nature, states of nature.
Yes, although this is kind of an abstraction. So basically, any definition of state that's Markovian will satisfy this. Okay, so a general scheme for an off-policy Q-learning algorithm, just a very general template, might look something like this. You collect a large data set of transitions, states, actions, next states, and rewards from some policy, maybe some exploration policy or some random policy. You put it in your buffer, and then you continuously go through your buffer, sample a batch, minimize the difference between the Q function and that Bellman backup on that batch, and then repeat this procedure. And you can repeat this procedure just like you do stochastic gradient descent many, many times, and then occasionally you go back out into the world and collect a little bit more data. So graphically, this looks like this. You have the world, you collect your transitions from the world, put them in a big buffer, run your Q-learning on that buffer, and occasionally go back out and grab more data. Okay, this is an algorithm that has been known for decades, and it's a very reasonable place to start. So in fact, we've had some experiments in the past that applied a variant of this, a continuous variant called normalized advantage functions, to do things like real-world door opening with robots. And you can get it to work. You can actually get it to learn complex skills in real-world settings. So what's the problem? Why aren't we done yet? Why isn't everybody using this approach, this Q-learning approach that's been around for decades? Well, off-policy reinforcement learning has a number of huge challenges. One challenge is that it's not very easy to get convergence results. In fact, the Q-learning algorithm with function approximation using things like neural networks does not in general converge, not in theory and not in practice. You can get it to converge by essentially torturing the hyperparameters until it works right, but this is quite a time-consuming and onerous process. And as a result, these algorithms tend to be very sensitive to hyperparameters, which is trouble for this guy. Sample complexity is sometimes good and sometimes not so good. So it seems like it's a little difficult to get, again, both theoretical and empirical consistent results that indicate these algorithms are actually efficient. So for example, if you want to learn to play the video game of Pong with Q-learning, you can do that, but it will take you 2 to 10 million frames at least. And this is actually one of the easiest games you can learn. Many of them will take millions more. And some algorithms are more off-policy than others. And this is another thing that's also very hard to quantify. It's just how off-policy can that off-policy data be? Is it really the case that you just collect a large bucket of data? Or is it just the case that you're using slightly older data than usual? And again, algorithms vary all over the place in this regard, and it's very hard to develop sort of a consistent idea about which one will be which. And there's also lots of really nasty local optimum in reinforcement learning problems. I'll illustrate an example of this on the next slide. So I'll tell you about an algorithm that we developed that where we thought we were going to mainly be addressing the problem of local optima, but it turns out that it actually makes a little bit of progress on addressing every one of these points. And I'll explain a little bit about why that might be the case in a second. So we started by thinking about the local optima issue. And we can illustrate this with a very simple example. This is a little 2D walking robot. And what you're seeing here are two videos of that robot walking. Both videos are produced using the same algorithm, the same reward function in the same environment, and the only thing that's different between them is the random seed that was used to initialize the algorithm. And it results in two gates that are both successful, but they both look very different. So it's pretty unlikely in this environment that both of those gates are actually optimal, and in fact they're not. And the same thing happens with a more complex scenario. This is a humanoid robot, again, two different runs of essentially the same algorithm with just different randomness, and you get pretty different behavior. So we can set up a little kind of microcosm of this issue just for our own understanding in a little simple maze environment. So here you have this little spider robot, and the spider robot needs to reach the blue square. And it can attempt to reach the blue square by exploring either the upper passage or the lower passage. Now in reinforcement learning, when your agent starts receiving rewards, it prefers to visit those states more often. So if the spider randomly chooses to go to the upper passage initially, it'll see that it's getting closer to the goal, and that behavior will be reinforced, and it will do that more and more often until it has completely forgotten about the lower passage, gets to the end of the upper passage, and gets stuck. So the right way to try to address this environment is to track both hypotheses simultaneously. And there are a number of methods that explicitly try to tackle the problem of exploration with a variety of techniques, things like Thompson sampling and exploration bonuses and so on. That's not actually what we're going to be concerned with. We'll be concerned with specifically off-policy reinforcement learning algorithms that inherently can avoid this issue. So remember, the solution here would be to track both hypotheses simultaneously. So how can we do that? Well, remember, in Q learning, you learn a Q function which basically tells you what's the total reward that you'll get if you take a particular action in a particular state and then act according to your policy, or for the optimal Q function, act optimally. Once the Q function is learned, you recover the action by choosing the action that maximizes the Q function. So in this little spider environment, at that initial state, the Q function will typically have two peaks. If you've explored both passages a little bit, the peaks will be low. If you explored them a lot, the peaks will be high. If you've explored one more than the other, then that peak will be a bit higher than the other one. Initially, arbitrarily, one of them will be just a little bit higher than the other because of noise, and then you'll select preferentially that higher peak, and you'll explore that passage more often. So this will cause you some trouble. What you can do instead is you can commit your probability mass in proportion to the height of those peaks. In particular, there's a very nice probabilistic interpretation of what happens if you commit your probability mass in proportion to the exponential of the Q function. I won't go into the details of that, but the intuition is that you want these probabilities to be positive, and you want them to sum to 1. So if you make it proportional to the exponential of Q, that ends up working actually fairly nicely. Now what will happen is that if the two peaks are about equal in size, you'll actually explore both of them until you find that one is much better than the other, and then you'll commit most of your probability mass to that. Now, one problem here is in continuous action spaces, actually sampling from this distribution is very difficult because it can be complex and multimodal, like in this example. So one of the things that we did in this work is we figured out how we can adapt algorithms for implicit generative models. These are algorithms that transform a sample of Gaussian noise into an unbiased sample from some more complex distribution like this exponential Q. There are a variety of ways to do it. The particular one we used in this work is based on something called Stein variational gradient descent, but there are other techniques you can use based on things like GANs and so on. Many of these are developed for generating images, basically synthesizing images from scratch from noise. But here we can adopt them for sampling actions that follow this exponential Q distribution. So now, remember, in regular Q learning, once the Q function is learned, you take the action according to whichever action maximizes the Q function. And this can be shown to maximize the RL objective of the total expected reward. A reasonable question we can ask here is that, well, what kind of objective are we optimizing when we choose our actions according to this exponential Q distribution, right? Because in the end, your final policy will still be stochastic. It's not going to converge just one deterministic decision. It turns out that you can show that if you do this, what you're actually optimizing is a maximum entropy reinforcement learning objective, an objective that maximizes the sum of rewards plus an entropy term. What this means intuitively is that the method is trying to find a policy that gets the largest reward while being as random as possible. So if a particular decision matters a great deal, then you'll be more deterministic. But if a particular decision does not greatly affect your reward, you'll break your tie randomly instead of choosing one decision arbitrarily. This alleviates things like this problem with two passages, but it actually has a number of other benefits that are a bit more subtle. It turns out that these kind of maximum entropy methods actually improve robustness in the face of unexpected perturbations. The intuition here is because you're not committing to any single hypothesis about your model, you're actually choosing them at random. That improves your robustness. Of course, it improves exploration, as I mentioned before. And surprisingly, it actually leads to more stable learning, which is what we wanted all along. So let me illustrate this with a few empirical examples. This is a video of a robot, a robotic arm, learning to stack Lego blocks using the soft Q learning algorithm that I described on the previous slide. The robot starts off not knowing anything about its environment. It's simply applying random torques on the arm. There's a little safety barrier that keeps it from breaking anything, but that's about it. The reward function tells it to stack the Lego block at the target location. So initially, it's moving around at random. Around 30 minutes into the learning process, it can already figure out how to get roughly in the vicinity of the target block, and occasionally actually puts it on, but only when it gets lucky. About 60 minutes in, it can stack the Lego block with a pretty good success rate, about the majority of the time. And after 2 hours, it can do it every time. This by itself is not actually all that interesting. You know, we've had RL algorithms that can learn to stack Lego blocks with real physical robots using deep neural networks for several years at this point. What's interesting is that once it has learned this behavior, we can have the mischievous graduate student come in and mess with the robot a little bit. So this guy's going to come in and he's going to try to basically give the robot a hard time, give it some trouble. Now, remember that the policy learned to maximize reward while also maximizing entropy, which means that it actually adapted to random perturbations that it itself was injecting during training. And that actually results in a policy that's very robust, so that when the mischievous grad student comes in and perturbs the robot, even in a fairly drastic way, you can still figure out a way to recover and solve the task. You can do other interesting things with these kinds of policies. You can actually compose multiple policies learned with soft Q learning. This is something that's not typically possible with regular Q learning algorithms, but it is with soft Q learning. So you can learn one policy for stacking a Lego block, one policy for avoiding an obstacle, add the Q functions together, and you can actually show there's a bound between that and the Q function that solves the combined task. And when you round on the robot, indeed, it can actually both avoid the obstacle and stack the Lego block. We can, excuse me for a second. We can modify the algorithm slightly to extend it into an actor-critic setting. And in that case, you actually get a very stable algorithm that performs very well in a range of benchmark tasks. So what you're seeing here is a standard reinforcement learning benchmark task called the half cheetah. The job of the half cheetah is to run as fast as possible. Initially, it does things like, fall on its face, but after a while, it learns to run. Oftentimes, when you see videos of deep reinforcement learning algorithms solving the half cheetah task, what you're seeing is maybe the best random seed if the algorithm is not so great. Sometimes you're seeing maybe the average random seed. This is actually the worst random seed for an actor-critic variant of soft Q learning. And the worst random seed actually already achieves state-of-the-art results on this task. So one of the things that we're kind of surprised by, but that's, I think, quite promising for off-policy reinforcement learning, is that the stability, the consistency of these algorithms across random seeds tends to be very good. So what you're seeing in this plot is soft actor-critic, which is the actor-critic version of soft Q learning, shown in red, and the pale lines in the background are runs for different random seeds, compared to DDPG, which is a state-of-the-art deterministic actor-critic algorithm, and TRPO in green, which is a policy gradient algorithm. And you can see that DDPG, it does pretty well in this task, but the individual runs are highly variable among themselves, whereas all the soft actor-critic runs are fairly tightly clustered. And the soft actor-critic algorithm can also learn to stack Lego blocks. Okay, so by no means are the issues with off-policy RL actually solved. I think this is like a small step in that direction. But hopefully one of the things that I've convinced you of is that if we look a little bit more closely at how we can develop algorithms that address some of the difficulties of off-policy RL, we can make some progress on stability, on exploration, and so forth. Now let's talk a little bit about how deep reinforcement learning algorithms can be brought into the real world, how we can generalize from real-world experience. So remember, I mentioned that one of the advantages that we should, in principle, have from off-policy reinforcement learning is to be able to train it on large and diverse data sets. So the kind of tasks that we typically use for benchmarking in reinforcement learning, well, they look kind of like this. They're small and uniform. The goal is typically mastery. It's basically testing your ability to optimize your objective function. And the test set is identical to the training set. So these are the settings where most of these algorithms are developed and tested. The real world doesn't look like that. In the real world, everything is huge and highly varied. The goal is not really mastery, it's just kind of generalizing effectively. Basically, don't mess up too much, achieve some baseline level of performance everywhere. And the test set is an unmitigated disaster of complexity. You're going to always get the unexpected. You're going to get things that are highly varied and diverse. And this poses a huge challenge for these kinds of methods. So one empirical experiment that we did at this point about 2 years ago is to see how we can perform self-supervised learning, off-policy learning, at sort of ImageNet scales, the data sets with the kind of size and complexity of things like ImageNet. So what we did is we set up a laboratory with a number of robots that were all cooperating together to collect a large data set of experience. And all these robots are actually jointly trying to solve a single task. They're trying to solve the task of grasping. But now, instead of just grasping one object, they're actually trying to grasp any object that's placed in front of them using observations from a monocular camera. So in total, this thing ran for several months, collected about 1 million grasps. And then afterwards, we wanted to see, well, when you train a policy on this kind of data, what kind of behavior do you get? Do you actually get interesting generalization? Do you get systems that show emergent behavior that is perhaps surprising, that's different from hand-engineered systems for these kinds of problems? So this is a video of the learned policy after about 1 million grasps. And what I'm going to show you here is this policy grasping objects that all are basically rectangular and blue. They're kind of roughly similar in appearance. And for the rigid objects, it does pretty much what you expect. It puts the fingers on either side and picks up the object. It does it for this eraser also. But the next object that you'll see is, it's also the same color, roughly the same size, but it's a soft sponge. And for the soft sponge, what the robot does is it actually pinches it in the middle. And this isn't an accident. This is actually one of the first patterns that this policy learned, is that soft objects can be pinched while hard objects can't be. A few other things it learned to look for the center of mass, because grasping something near the center of mass makes it less likely to fall out of the gripper. For a small object, sometimes it takes a little while to find a good grasp, repositions the fingers a few times, but eventually finds something for which it predicts high probability of successful outcome and picks it up. Okay. We can also do experiments like this for robotic mobility. This is an example of an experiment done by Gregory Kahn and Adam Villaflor on self-supervised learning using, again, a variant of Q-learning for autonomous navigation. So this robot, this little RC car, starts off doing fairly silly things. It runs into things. But as it does that, it's recording monocular images from its camera and collision detection from its accelerometer. And what it's learning to do is predict if it takes a certain pattern of actions, will it experience a collision based on what it's seeing from its monocular camera. And after running this for a few hours, it can actually navigate a single hallway. If you run in a few hallways, then it can navigate a variety of hallways. Okay, can we go a little bit further? So far, we talked about how we can learn a single skill from a lot of experience of that skill, highly varied data. But if we have very large data sets from a variety of behaviors, what can we really get from big data sets of past interactions where it's not just a single skill? So we'd like to get something that's task agnostic, something that we can use broadly in a variety of circumstances for a variety of different behaviors. So what about learning something about physics? What about, instead of learning to predict the outcome for a particular task, what if we learn something that's sort of universal to the environment? So one of the projects we've done to explore that is to set up a self-supervised learning experiment with model-based reinforcement learning, again using camera observations. So the setup here is that robots will interact with their environment, record what happens, literally record videos and their actions, and then learn to predict future observations conditioned on their actions. And if they can do that, then a user can come along and say, I'd like you to achieve this, and the robot will predict the outcomes of possible actions and pick the ones that actually achieve the user-specified goal. So the training phase looks like this. Well, this is a person, not a robot, but if you have a robot, then it looks pretty much the same idea. It looks like this. You have a robot that's playing with objects in its environment. Here, it's playing completely at random, although you could use a more structured exploration scheme. It's recording the videos of the interactions that took place and also the actions that it executed. And when it collects this data, it can use it to train a predictive model, a model that actually predicts future image observations conditioned on what it's seeing now and the actions that it will take in the future. So once that model is trained, a person can come along and say, I'd like this object over here, indicated in red, to be moved to this other position over here, indicated in green. And these are objects that the robot didn't see during training. And now what the robot can do is it can use its predictive model and can ask, if I choose different actions, what will I see next? So what you're seeing in the top row here are actually predictions from that model for different actions. So you can see that if it predicts what will happen if it moves right, the R moves to the right, and the object kind of follows, and so on. And the bottom row is showing the predicted movement of the point indicated in red, the point that the user specified. So here the robot might choose maybe the second or third action because that seems to be moving the red indicated pixel to the green location. Now remember that here, the system was never told anything in advance about what are objects or what is physics or collisions or anything like that. Everything has to be inferred from pixels by learning to predict those pixels. So If we actually do this for this simple disk example, it does pretty much exactly what you expect. So it figures out that it should approach the disk, push it to the location, and so on. This is fairly simple. It can also do more complex tasks. So here we're asking it to push the stapler to the location indicated in green. Again, these are novel objects that the system hasn't seen before, and it has to do this directly from raw image pixels. So it actually makes a prediction that says, well, I'll go out and I'll actually grab the stapler and I'll push it. And when you actually run it on the robot, indeed, that's what it does. It goes out, grabs the stapler, puts the fingers around it, and pushes it to the target location. Now, because everything is done from image pixels, we don't really care whether the objects are rigid, whether they're governed by equations of motion that we can write down. We can, for example, give the robot a soft deformable object, which ordinarily would be pretty hard to model, and it can figure out how to go out and push this little oven mitt. Okay, so if we can predict observations, we can do that from large amounts of data, even data collected for other tasks, and then use it to synthesize new behaviors. All right, let me now talk about the last topic, which is making all this happen more quickly by learning to learn. So far I've talked about how we can use past data to learn efficiently with model-free off-policy RL, how we can use past data to generalize better with these large-scale robotic experiments. But the last question I'm going to study is how can we use past data to actually learn new tasks more quickly? Beyond just generalizing to new tasks more effectively, can we actually use past experience to learn something about the process of learning itself? Can we learn to learn? So one framework that can allow us to get a grip on this idea is the framework of meta-learning. This is an illustration from a paper by Ravi and La Rochelle that I think very nicely illustrates the basic supervised setup of meta-learning. So the setup here is that in contrast to supervised learning, where you learn to map from inputs to outputs, in meta-learning, your goal is to train a model that, when exposed to a small training set, does well on a corresponding test set of that task. And the way that you can do it is you can construct a meta-training set that itself consists of a collection of little data sets. So let me go into this in a little bit more detail. In standard supervised learning, your goal is to learn a function that maps from some input x, which might be, for example, an image, to some output y, which might be the label of that image. In meta-learning, at least in supervised meta-learning, it's a very similar idea, except that now your function maps from a training set, a little training set, and an input, to the label for that test input. So for example, you might see a little training set that shows 5 pictures. One picture is labeled dog, another picture is labeled cat, and so on. And then you're shown a new picture, and you have to figure out that it's cat. And then at meta test time, you might see a new little data set with images and classes that you've never seen before. So your goal is to train a model that can basically accurately match this function f. Some previous work has done this, for example, by training recurrent neural network models, essentially inspired by successful sequence models, which can already ingest variable size inputs, so that you can set up a sequence model that maybe ingests the little training set, x1, y1, x2, y2, x3, y3, and then essentially contains in its hidden state the information it needs to classify a new test input x. This is something that was, variants of this idea have been explored in a number of previous papers, including more clever architectures based on things like temporal convolutions. So essentially this little first part is your few-shot training set, and when you say that the algorithm is learning to learn, the learning at meta-test time is happening inside the RNN. So the activations of the RNN are sort of what it learned about the few-shot training set. So this is a reasonable way to go about meta-learning, but we thought about this problem a little bit and we thought, well, maybe there's a simpler way to do this. Maybe there's a way that we can come up with an algorithm that doesn't require training complicated sequence models or RNNs, but still achieves good performance for these learning-to-learn problems and can be used in a reinforcement learning setup. So this is work that was led primarily by Chelsea Finn, and the idea here is the following. Let's say that you have a regular reinforcement learning problem. Maybe you want to get this little spider to run forward. You'll generate a few samples of the spider running forward. You'll compute, using those samples, the gradient of the reward with respect to your policy parameters. You'll apply that gradient, so this is kind of the usual thing that we all know about. You'll apply that gradient, you'll get a new parameter vector that hopefully does a little bit better in terms of its reward. Now in the meta-learning setup, during meta-training time, the spider might attempt to run in lots of different directions, and you need to use this experience not to learn a policy that runs in all directions, but to learn a policy that can quickly learn new tasks, quickly learn to run, for example, in new directions. So we looked at this update and we thought, well, this is a pretty good way to update your policy. Like, we all understand how policy gradient and gradient descent and so on works. Let's try to use that inside a meta-learning algorithm. Let's actually optimize, not for a big recurrent neural network, but for the same exact kind of feed-forward policy, except that now we'll optimize for that policy to adapt quickly. We'll say, when you want to adapt, you'll adapt using a gradient. So let's find a vector of policy parameters that, when adapted via a gradient on a particular task, improves as much as possible on that task. So this doesn't mean that you're trying to find a policy that does well on all tasks simultaneously. In fact, the actual parameter theta that you optimize here might do very poorly on all the tasks, but it's optimized so that after you apply a gradient for that task, your performance on that same task improves as much as possible. So this is a policy that is optimized for fast adaptation. There's no additional modification to the architecture. There's no change in the neural network. There's no recurrence or anything like that. It's just the same kind of policy. It's just optimized differently. It's optimized so that it will adapt quickly via gradient descent. So we can visualize this idea graphically. Here, the thick line with the arrow indicates the path of theta through the parameter space. And at every single iteration, you see how gradient updates on each individual task might change your policy parameters and move the entire parameter vector so that these updates move you closer to the optimal parameters for each of the constituent tasks. So you're optimizing a policy that can adapt very quickly. And you can do this with more than one gradient step. In practice, you would typically want to use 5 to 10 gradient steps in the inner loop. So let's illustrate how this method actually performs on an example few-shot reinforcement learning task. First, we'll look at the policy parameters that we learned via this meta-learning procedure. So these are not the policy parameters that are good at any one task. These are policy parameters that are good at adapting. In this case, adapting to running in different directions. So if you visualize the resulting policy, it doesn't actually run in any direction successfully. It sort of runs in place. This is kind of what you might expect. This is a policy that's ready to learn. It's ready to learn to run, in this case, in any direction. And then if you give it, in this case, just a single policy gradient update with a reward function for running forward, this is a pretty simple task, so a single update is enough. It'll actually figure out immediately how to run forward at a pretty fast clip. And again, if you give it a reward for running backward, the same policy parameter vector will figure out how to run backward in one gradient step. Now, this approach, we call it model-agnostic meta-learning because it's agnostic both to the architecture of the policy and also actually to the loss function that's used. So you can use a reinforcement learning style loss function as I did in those examples, or you can use the same exact method with a supervised learning loss function. So at the time that this paper came out in 2017, it actually achieved very competitive results with few-shot meta-learning approaches that were designed for image classification on few-shot image classification benchmarks. So the same exact idea, just doing these inner gradient steps and optimizing for parameters that adapt quickly with gradient descent actually works across a range of different problem settings. So a reasonable question we might ask is, well, why does this work? So remember, in the RNN-based meta-learning approach, the idea is that you would design some kind of neural network architecture like a recurrent neural network that ingests the little training set and a test point and makes a prediction for that test point. So essentially, this first part, the recurrent part, is the implementation of your learned learning algorithm. So your learned learning algorithm is a forward pass through this RNN. Now, if this is a learning algorithm, we can ask questions about it. We can say, well, does it converge? Well, the answer is yes, kind of, because it's just a forward pass of an RNN. So you run the forward pass, it's done, and you get your activations. What does it converge to? Well, nobody knows, because it's the entirety of the learning algorithm has to be learned inside the RNN procedure, and it does what it does, and there's not really much more that you could say about it. And what do you do if it's not good enough? So you take your little training set, you run a forward pass to your RNN, it produces a prediction, and you're not happy with that prediction. What happens then? Well, again, nobody knows because it was trained for that particular forward pass. If the answer that it produces is not good enough, you can't just run the learning algorithm for longer. It's a forward pass of an RNN. With model-agnostic meta-learning, the story is a little bit different, right? Because now the training set is being fed directly into this gradient descent procedure. So does it converge? Well, yes, in the same sense that gradient descent converges. So it will converge to a local optimum provided an appropriately chosen learning rate and so on. And what does it converge to? Again, converges to a local optimum provided you do everything right. And perhaps most interestingly, if it's not good enough, you just run it for longer. Because in the end, even if you get inputs that are outside of the distribution of what you meta-trained on, it's still a gradient descent procedure. So if you just run it long enough with enough data, it will eventually do its job. And the only thing that you might lose if you're too far out of distribution is the benefit from the meta-training. So it's a graceful degradation. And in fact, experimentally, we can do some experiments and show that indeed this does happen on out-of-distribution tasks, that it gracefully falls back to regular gradient descent. Now, another question you might ask about this procedure is that, well, we know that the RNN is a universal function approximator, meaning that if this RNN is big enough, it can eventually represent whatever learning algorithm you want. It might take a very large amount of data and a very large number of weights, but eventually it can do it. So we might ask, well, for mammal, is that also true? Because it seems like it's a bit more limiting. All it's doing is this gradient descent. Maybe it can't represent any update procedure. it turns out that you can actually show that for a large enough neural network, this kind of learning of a good initialization for gradient descent can in fact represent any permutation invariant function of the training set and the input. This requires potentially a very deep neural net, but you do in fact have the same universality here as you have over here. Okay, let me wrap up by showing a few examples of applications of this meta-learning algorithm. One of the things that we've applied it to is few-shot learning of robotic skills from demonstration. So the idea here is we would like to illustrate a behavior to a robot just once and have it figure out what is the goal of that behavior and reproduce that behavior in new settings. For example, we might show the robot, I want you to put the apple in this bowl over here, and then we move the bowl around, and it has to figure out that indeed the apple has to go in the bowl and not on the plate and not in the other thing. So the tasks here for this experiment, they'll all be chosen to be placing tasks, just for the sake of keeping things kind of contained so that we can do this with a reasonable amount of data. So placing different things into different containers. And then at meta-test time, the robot will be asked to place a new object that it has never seen before into a new container that it hasn't seen before. So this is what meta-test time looks like. The robot receives one demonstration. In this case, these are via teleoperation. So there's an operator behind the scenes with a virtual reality rig showing the demonstration. The robot observes this demonstration using its camera. And then it has to update the parameters of its policy that has been meta-trained to update quickly. And then has to figure out that when the blue bowl is moved around, it has to put the apple actually in the blue bowl and not somewhere else. So it has to recognize what is the intent of this task. Now, this is perhaps not all that useful because you still need a teleoperation set up to actually illustrate the task to the robot. What we'd really like to do is we'd like the robot to figure out what it's supposed to be doing just from watching a person do the task. So it turns out that we can actually extend this idea to a setup where we have just a video of a human and not a teleoperated demonstration at meta-test time. So remember that in model-agnostic meta-learning, the way that we meta-learn the policy parameters is by training theta so that after a gradient update, it performs well on the task. So for every task at meta-training time, we have two demonstrations, a training demo that is actually used for the gradient update, and a validation demo, and the robot is asked to do well in the validation demo after updating on the training demo. And then at meta-test time, you just have one demo, and you just do the update. So what we'd like to do is we'd like to get this demo at meta-test time to be just a video of a person. The trouble with a video of a person is that you don't have supervision. You don't know what actions the person was taking. You just have a video. So what we can do at meta-training time is for every task, we have a validation demo that is still from teleoperation and a training demo that is a video of a person. And the loss function for the training demo is actually itself a learned neural network. So the loss function here uses temporal convolutions to map a video to a scalar value, which represents the loss. And that loss is trained via the meta-learning objective. So you basically learn the loss such that when you update via that loss, you do well in the corresponding validation demo. And then at meta-test time, all you need to show the robot is a video. So here's what that looks like. Here is Kevin showing the robot a demonstration. He wants the peach to be placed in the bowl. The robot is going to watch this video. This is meta-test time, so it's going to update the parameters of the policy via gradient descent, via that learned loss function. And then Kevin can go in, move the objects around, and the robot has figured out that, in fact, the peach needs to go in the red bowl. Okay, so in summary, I talked about how we can develop better off-policy reinforcement learning algorithms, perhaps ones that are more robust, ones that are more resilient to perturbations, how we can generalize from large amounts of real-world experience, and how we can actually make it all happen quickly via meta-learning. So lastly, I'd just like to thank the students that actually, oh, how convenient.